Okay. So we started trees yesterday and talked about the classical result of Feynman and Pippinger about embedding a moderate size tree with bounded degree into some graph with expansion property. So let's recall that. So this is, where is it? Theorem 5.1. It says that we use this for the external neighborhood, okay? No, sorry, for just the neighborhood. It says that if we have, for all small sets, up to twice the size of the tree we want to embed, we have this expansion property, okay? Then we will get all trees on m vertices and max degree d, MOSD. Okay, so we can get with expansion implies bounded degree trees with relatively large size m, but there's a upper bound on what m can be. So if you if you look at this statement, we can only get trees of order at most n over, if n is the order of the graph G, okay, 2 times d plus 1, because we need expansion for 2m, right? And it needs to expand by d plus 1, so we need to divide it by 2 times d plus 1. So that means we are even when d is constant, we are nowhere near finding a tree that's almost spanning, say, right? Or taking 50% of the vertices. So today we will briefly talk about almost spanning trees and start the proof for spanning trees, okay? In fact, almost spanning tree, we just need to write down the statement because the proof we've seen, it follows basically from yesterday's technical lemma that we've seen, okay? And the interesting part is the spanning one. We will get to it. So let's first talk about almost spanning ones. So to talk about almost spanning one, maybe it's good to rewrite consequence of lemma 5.4, the technical lemma. Rewrite them in different forms that's easier to apply. And recall lemma 5.4 says that if we have some certain expansion property, roughly speaking, then you can embed bounded degree trees one leaf at a time and make sure that every step of the embedding, all the partial embedding at every single step has some nice property, right? There are enough room for you to extend it further. Basically, that's what lemma 5.4 says. So if we re-examine the proof, examine the proof of the Feynman-Pippinger that I gave yesterday, actually exactly the same proof, identical proof. If you read through the proof, we get the following, which allows us already to get larger trees than G over 2 times D plus 1. So formally, we let D and N to be some natural number. And suppose we have G satisfies the following, okay, expansion property. What are the expansion? Well, first of all, Small sets expand by a factor of d as usual. Plus 1, okay? For any x of size smaller than m. And we require largest expansion for x between 2m and m. We require a slightly larger expansion. Then the conclusion is that G contains any tree T, okay, for any T with order and most T vertices and maximum degree, bounded degree again. Okay, so for example, you can think of T as 1 minus 0 1 times n, almost spanning. Say n is the order of the graph G. Then this basically says that for small sets, if we have expansion factor d, and for large sets, our neighborhood touches almost everything, then we can embed the almost spanning tree, right? If you stare at this second condition here, this is basically equivalent to this large set expansion that I've mentioned in one of these exercises that we define large set expansion, saying that when you have a large set, in this particular case, by large we mean m, between m and 2m, then your external neighborhood is huge, okay? And we've seen previously that random graph with sufficiently large probability, they satisfy this natural property. Okay, so here, a remark, just to write down what I just said. If T is 1 minus 0, 1 times n, where n is G, then this is basically, not exactly, but basically this large set expansion property we've seen from exercise 4.4, okay? And also it's basically the same as this large set connectivity, the M joint, meaning that two sets of size M, there must be an edge. These two are roughly equivalent. Let me just put a remark here. If it's not immediately clear to you, just draw some picture and you will see. It's roughly also the same as large set connectivity. It's convenient to give some name to it. So when we refer to this, basically you can refer to definition 3.3 for the M joint thing. All right, so these are actually natural conditions to impose on when we're dealing with random graph. And sometimes it's also, so this is the same proof as theorem 5.1, 5.6, which allows us to embed almost spanning trees. And sometimes it's also convenient to phrase in terms of expanders. Okay, so in terms of expander, we can write it as follows. So this is basically, we're going to write a consequence of 5.6. So in terms of expander, can be written as expander plus large set connectivity as in definition 3.3. Recall this. What is large set connectivity? If you don't quite remember, it basically just says that if you have two sets large, say M, then you must see an edge, at least one edge between them. Okay, that's the large set connectivity. Okay, all right. If you have these two, then basically, okay, now the pen gets thicker. Expander plus large connectivity gives you all bounded degree, almost spanning tree. Okay, let's write it. This for this we define some notation. In fact, we're not just get the one given tree. We get all trees like this. So it's convenient to define for integer t and delta. We define this to be all t vertex trees with max degree and most delta. Okay, bounded degree t vertex trees. Then we say a graph is t delta universal if it contains all these trees from this family. Okay, it contains a copy of all trees in this family. So we get actually everything. In this notation, we can now state 5.7. It's just a consequence of 5.6. You play with the definition of the expander. It's easy exercise to derive it from 5.6. So it says that, okay, we're given D is at least 2 delta for some fixed delta, okay? And we have that G satisfy its n over 2D joined. This is the large set connectivity. Every two set of size at least n over 2D, you must see an edge in between. And you are, sorry, G is a D n over 2D expander. Okay, this means for every set up to size D, it expands by a factor of D. Sounds a little bit strange. Am I doing it right? Sorry, yeah. Of course, I swapped the order. For every set up to size n over 2D, it expands by a factor of D. So you grow up to size n over 2, right? If you grow by factor D. And after that, we don't necessarily guarantee expansion factor D. But up to n over 2D, you expand by a factor of D. This is the notation. So yeah, as I said, we have the expansion. G is expander plus large set connectivity. Then G is, and D is at least 2 delta. Then G is T m minus 4 delta times n over 2D delta universal. Okay, so if you imagine delta and D to be constants, say, then we have n minus some little n. It's almost spanning, right? Of course, you're free to choose D and delta to be other parameters, so you can find smaller trees as well. All right. So, okay. Now we can talk about, I want to briefly also talk about almost spanning trees. Since these are the same proof, so I skip the proof. Just look at proof 5.1, you get the same 5.6. And 5.7 follows by definition of the expander and this high connectivity, large connectivity. So let's look at almost spanning trees in GMP, in random graph. If you want almost spanning tree, first of all, we need P to be at least some constant over N, okay? Note that when P is less than 1 over N, even by an epsilon proportion, then almost surely all the connected components, all the components in GMP, they only have logarithmic size. This in the literature is so-called when we have a giant component, giant means linear in N, I think. So when you go beyond 1 over N, then suddenly you see a huge component. But Below that, you have all the components, they are small, okay? Then almost surely GMP has only small component, okay? Logarithmic size. Now, so that means the best we can hope for is P is at least some constant times C. And we've seen previously last week that when P is at least C times N, for large N, we get almost spanning, not so, recall. We get almost spanning cycles. So there's no obvious reason we cannot get, say, bounded degree tree. They are, in the sense, simple structure subgraphs. And this is indeed shown by, first, shown by Alan along Krivelovich and Sudakov, that the threshold of almost spanning tree is constant over n, okay? All the trees are bounded degree, if I didn't write it specifically. Bounded degree trees is 1 over n. In fact, they show that not just a given tree, you have the universality, meaning that when you go beyond C over n, you get a copy of every bounded degree almost spanning tree. So this is theorem 5.8. We let more precisely, okay? We say epsilon is the leftover, and delta is the degree for the tree. There exists some constant sufficiently large, depending only on epsilon and delta, such that almost surely GNC over n is 1 minus epsilon n delta universal. Once again, it says that what it means is that if you give me any tree with maximum degree delta on at most 1 minus epsilon times n vertices, then with probability 99.9, I can find you this tree in GNC over n. Okay. So to prove this 5.8 basically follows quite straightforwardly from 5.6 that we wrote down here, the expander version. Because by 5.6, setting t to be 1 minus theta 01 times n, all we need to do for this threshold for almost spanning tree is to show that when P is at least C over n, we have this two expansion property. We have the expansion property for small sets, and we have this large set expansion property for sets between size m and 2m. These are fairly straightforward to verify. Okay, let me see if it's worth writing it down. How much time I have? 20 minutes, 40 minutes. Okay, I think the proof is simple enough to write down. Let me I skip lots of basic things. Maybe I do this one. Proof. Okay, so I will write some essential steps. We will take, of course, C to be sufficiently large compared to epsilon and delta. This is what it means, okay? We take sufficiently large C compared to epsilon and delta. And by Chernoff inequality, we can get this large set expansion This is basically large set expansion. Okay, it says that for any X subset of size M, which I set M to be some log 1 over epsilon over C times N, okay, if you take M to be something like this, then almost surely we will see that it expands. The neighborhood is almost everything. Okay, you external neighborhood touches almost everything. This is very standard. We've seen it in exercise 4.5 or 3.5, something like that. Now, with this simple property, then all we need to do is to show that small set also expand. Because to apply 5.6, let's see it again. We have the orange box already. That's the large set expansion. Now, for the first condition, we just need to show that small set also expand by a factor of d. And to do this, we've actually done it before. When you have large set expansion, you can bootstrap it to small set expansion. Okay, this is in one of the exercises that I gave before. Now we bootstrap large set expansion to all small set expansion. This is similar to claim, for example, 4.7, which I left as exercise. So meaning that we want to find W, okay, such that small, such that G minus W has small set expansion, has this property, first property in 5.6. The external neighborhood expand by a factor of d for all small set up to size M. Okay. So if you've done the exercise, good. If you're not, let's do this again. This is very simple. If you just want to a weak bound on W, remember that when we do Hamiltonian cycles, we have to be more careful, removing as few vertices as possible to make it expander. So at that time, we do a lot more complicated things, the technical lemma we shown last week. But now we just need a weak bound on W, so we can do it fairly easily. So what we do is that it's a standard trick, okay? Proof of this claim. Take W such that it's a maximal set under inclusion, and such that W is at most 2M, and such that it does not expand well. Okay, so to bootstrap it, basically we say that if the graph does not have small set expansion already, that means there is some small set that does not expand well. So let's grab one such set, call it W, and make it a maximal one. Okay, then we claim that G minus W must have small set expansion. In a nutshell, the reason is that if G minus W, after removing these poorly expanding sets, the remaining graph does not have small set expansion, that means you can find a small set that expand poorly. Then combining this small set together with W give you a larger set under inclusion that expand poorly. That contradicts to our choice that W is maximal, right? So let's quickly see this proof and jump to the next topic. So how do we do that? Well, first we claim that W, in fact, under this condition, it must be less than M instead of 2M. Okay? Not just M. This is basically large set expansion, because otherwise, if W is at least M, what you can do is you take W prime in W, right? And look at the external neighborhood of W prime. of size m. What do we know about sets of size m? Our hypothesis says that, where's our hypothesis? Here, right? Our large set expansion says that if you have sets of size m, your external neighborhood is almost everything. So that means our external neighborhood of W must be at least external neighborhood of its subset minus, we need external, so minus W. And W is of size at most 2m by our choice, right? So this minus is not too big. At least 1 minus epsilon over 2n. This is the large set expansion minus 2m, which is bigger than delta plus 1 times W. Because again, W is at most 2m. They contradict to our choice that W is poorly expanding. Okay, contradiction. So that means W has to be at most m. Now, suppose G minus W contains a set U that expands poorly, okay, such that U is small and its external neighborhood after removing W still does not expand well. Then what do we know? You just consider, then this implies that if you take the union of them, this is at most delta plus 1 times union of them, right? Together they expand poorly. But then where's the contradiction? U is at most size m. We just proved that W is less than m. So together they're still less than 2m. Satisfy this criterion here. Okay? So that means W was not maximum choice, a contradiction. This is the bootstrapping that I was talking about last week. All right, then the rest is just by applying 5.6. Then 5.6. I will skip the detail. Okay, a direct application of 5.6. We verified the hypothesis there. Good. I hope this is fine. I try to skip some boring details. Okay, so what I want to focus on today and tomorrow is actually the spanning bounded degree tree, which is a lot harder than this almost spanning one. As you can see, for this almost spanning one, all we did is the technical lemma yesterday, which is still kind of intuitive. It's kind of like an induction with stronger hypothesis kind of thing. But for spanning bounded degree tree, to find the right threshold, a lot more ideas are needed. Okay. All right. First of all, to talk about the threshold at all, we need to have a guess first. What will be the right threshold? So recall, we've just seen that in G and C over N, we can get almost surely almost spanning one. Right? The question is, can we just have spanning ones already? The answer is obviously no, because to have a spanning tree, a necessary condition is that the random graph has to be connected. And for the random graph to be connected, a necessary condition is minimum degree has to be at least 1, right? And all of this threshold is roughly log n over n. So we need much higher probability for spanning trees, as GMP needs to be connected. Okay, so this is a necessary condition. This happens when P is bigger than log n. We just need a little bit bigger. Okay, quite sharp threshold for this. This is in fact also the same threshold for minimum degree at least one. Maybe it's a good point. It's a good time to point it out that this is kind of like a local global phenomenon, right? So when you don't have the local obstruction, then you get some global structure. For example, here, when we stop seeing isolated vertex, so the minimum degree becomes at least one, it's not a sufficient condition for the graph to be connected, but this is obviously an obstruction. When this obstruction disappears, when you don't have isolated vertex, then almost surely, high probability, the random graph becomes connected. This is what I mean by local global. We've also seen it last week that to have a Hamiltonian cycle, a necessary condition is minimum degree at least 2. Or in other words, local obstruction is to have a vertex of degree at most 1, right? So it turns out that the threshold for both minimum degree at least 2 and Hamiltonicity are the same. They coincide. This is the local global thing. Okay, so this is necessary, and for a long time we don't know. We don't have we don't know if this is the right bound for the upper bound. The best bound before is by Krivolovich, which for bounded degree tree gives you roughly n to the epsilon over n. So up here, you put n to the epsilon. Well, it's tight up to, it's like n to the -1 + 1, but still so close yet so far, right? So a couple of years ago, this was finally resolved by Montgomery. So he proved that he showed that basically that's the threshold when we have he actually showed a universality condition. When P is some large constant over n, then you see all the trees of bounded degree. So he showed that there exists C, okay, which depends just on the degree of the tree. Then almost surely Gn C over C log n over n. The log is important. Is spanning tree universal with bounded degree delta. Okay. In other words, when the probability is beyond C log n over n, the graph becomes connected. We don't have obvious obstruction anymore. Then we start to see all possible trees, spanning trees with bounded degree simultaneously. This proof is quite involved and technical. It goes beyond this lecture series. So we will present a weaker bound. So we will show a weaker bound, weaker in two senses. One is we don't show for universality. We only show it for a given tree. Okay, for a given tree T. We don't do universality. And another way we weaken it is we don't prove log n over n. We prove optimal bound up to polylog factor. So it will show, for example, some polylog over n. Okay. So let me write it down. This is theorem 6.1 that we want to see. Let T be an n vertex tree with max degree delta. Then almost surely GMP where P is delta log n to the 5 over n. Delta is just some constant. Contains a copy of this spanning tree, of this tree as a spanning subgraph. Okay. This is what we want to see. For the proof of this, so what we will do is we will set up all the necessary ingredients for this proof and see that how we put these ingredients together to get these results. And tomorrow we dive into to see the proof of each one of these two major ingredients. That's what we will do. But before, okay, so any questions so far? Maybe it's a good time. The rest is a long proof that will take the rest of today and tomorrow. So if you have any questions about the statement or anything, it's a good time to ask. Otherwise, I will proceed from here. Good. So, so for this proof, basically, what we have to do is, if we go backwards, okay, what we have to do is we have to distinguish this tree T. So we're given this tree T, bounded degree. We have to distinguish it into two kinds. One we call leafy kind, one we call leggy kind. Let me define it, okay? So the idea...
on the setting.
Oh, okay, thanks. Let me see, where is the... Why we cannot derive the universality from a weaker bound only for given T? The reason is that suppose with high probability, you contain a fixed copy of tree on n vertex. Then to get universality, you have to take a union bound to contain all this tree, right? And the number of bounded degree trees on the n vertices, it grows exponentially with n. So that means you need a very strong bound on the failure of containing a specific tree. And that's oftentimes too hard to obtain sometimes, okay? So it's much harder. You have to apply union bound over all trees. So universality and the fixed tree is different. So not always, but sometimes what people do for universality is that I don't deal with random graph. I derive from random graph that with high probability is satisfy certain pseudo-random deterministic conditions. Then when you pass to deterministic graphs with pseudo-random conditions, and if you from there derive any given tree, you don't need union bound anymore, then you get universality. In 6.1, no, I don't believe so. Right. Okay. Good question. Now let's see what's the rough idea, and then we dive into to see each ingredient, how we get that. Each ingredient, I think, is interesting on its own. This is why I choose this result to present. And so where am I? We have to talk about the idea of the tree. So we have to distinguish the tree into two kinds, and we treat them differently using different strategy. This is what we do. We distinguish trees in two different kinds. One I call leafy, one we call leggy, okay? So it's kind of an intuitive name. What do I mean by that? So actually, it's not hard to say that for a bounded degree tree, for a tree, we have either lots of leaves, this would be the leafy case, okay? Or it has lots of bare path of long length. What do I mean by bare path? A bare path in the tree. So suppose this is our tree, right? and then here. This is a bare path. A bare path just means a path in the tree such that all internal vertices has degree 2. There's no branching from the internal vertices. That's the name bare, how it come from. Okay. So either you have lots of leaves, that's leafy, or you have lots of legs, right? The bare path. So one of these two cases. The following lemma make it precise. What do I mean by that? By equivalence. Very easy to state. It says that we lack n and k to be at least 2, bigger than 2. Okay, integers. Then an n vertex tree either has at least n over 4k leaves or at least n over 4k bare path, each with length k. So in particular, if you take k to be, in particular, n over 4k times k, that means the union of these bare paths constitute a positive proportion, 25% of the vertex sets, right? So you have either you have lots of vertices as leaves or lots of vertices sitting inside a bare path. Now, good. I will not prove this lemma. Now, how are we going to deal with these two different kind of trees? So the idea is kind of also intuitive. What we do is the following. For leafy trees, so what do we know? We know that it has lots of leaves, right? Then what we do is we're going to remove these lots of leaves. Remove leaves.
You have a question on the chatting?
Let me see. Where did Zoom go? A vertex disjoint. Yeah, good. They have to be vertex disjoint, right? Yeah, it's kind of implicit. Yes, vertex disjoint. Let me write it. Good. Yeah, I kind of just assume it. Good. It's vertex disjoint. Now, if you have lots of leaves, we're going to delete the leaves. And what's going on? Because it has lots of leaves, when you delete it, this tree is shrinked to 1 minus 001 times n size. Then we can use the almost spanning tree result just to embed majority part, right? So this is our T prime. We get T prime. Then we use the almost spanning. In particular, for example, this theorem 5.7 we just derived. Is it 5.7? Yeah, 5.7. It says that we have some large set connectivity and some expansion property for small sets. Then you contain some small sets up to size almost spanning. Then we can use this 5.7 to easily embed the majority part T prime. Okay. Then all it's left to do now is to add the star matching back to the right place, right? Now we have to add a star matching back.
You have another question on the chatting?
To get T, okay? How do I go to the, okay, here. The question is, maybe they can have a common endpoint. Okay, this is not so important. When they have, let's say they are vertex disjoint, okay? The bare path, a vertex disjoint. If they have, let's just say they vertex disjoint, this lemma. I didn't state it precisely. Now, where am I? Right. So you delete the leaf to get T prime. You embed T prime using theorem 5.7 because now it becomes almost spanning. Then you add this blue star matching back to T prime at the correct place where the leaves were deleted to get T. Okay, here you almost see the whole proof because the first step, removing, we just mentally remove it. The second step, you just apply 5.7. Of course, you have to verify the expansion property and large set connectivity, but that's standard to check using some concentration inequality. The last step, to add this matching back to the right place, basically, I will not write it down precisely. I think I'm running out of time. But basically, again, using expansion property, then the star matching, you blow up the center of the star to construct the auxiliary graph. Then a perfect matching there corresponds to a star matching. So all you need to do is to verify, to make sure that this auxiliary graph has large enough probability to have a perfect matching, which has threshold log n over n. But since we take log n to the 5 over n, there's lots of wiggle room. So we can make sure that this blue star matching is also very easily found to attach back. So this case is the simple case. All right. I hope I convince you on this because the rest is just basic things to check, the random graph property. Now, the interesting case is the laggy case. The laggy tree, it looks something like this. Okay. Maybe it looks ... You have lots of this bare path. Now what I do is that I will also delete, but I delete the internal vertices of this bare path. Okay. Internal vertices. So what you left is a forest T double prime, right? You remove internal of all this bare path to get T double prime. Okay. Then as usual, we use 5.7 to embed this almost spanning, to embed this partial tree, T prime, T double prime. This is immediately, you just apply it. That means how can one choke itself just by swallowing saliva? So that means the remaining task is to be able to find vertex disjoint path between vertex pair with given endpoints, and given ends and specify length. Right? So this boils the problem down to be able to cover the remaining graph with vertex disjoint path of given ends and specified length. So let me write this theorem down. It's taking longer than I thought. So it boils down to this theorem. Let me write it down. Which I call the following results, which covers an expander with path, right? This is what we want to do. We want to cover the remaining graph, which turned out to be an expander, not surprising because we're dealing with random graph. We want to cover the whole vertex set with the path. So precisely, this is theorem. Oh, this part, I don't remember the 6.7, good. The labeling is 6.7. It says that let n be, okay, we have n large And let's define L to be also large, some constant times at least log n squared. And let's suppose L divides n. All right. This is the setup. And then we assume that G is a graph, has n over L disjoint pairs of vertex sets, which you can imagine it as the n, this blue endpoints. We have some specified n's, x, disjoint x, I, y, I, n over L of them. And let's call W the remaining vertex. Okay. Now we suppose that G, I haven't defined these. I will define these to conclude today maybe. GD expands into W. I have not yet defined this, but just keep in mind some sort of expansion property towards a subset, towards a remaining graph W, where the expansion factor is fairly large, something like 10 to the 10, log n to the 4. This low order term doesn't matter, something like polylog n, a large polylog power, okay? Then the conclusion is that then we can cover the whole vertex set by x, y, y, x, I, y, I path, each with length L. Okay, let me draw a picture. So what do we have? We have x and y, and the remaining is our W. Okay. So there are n over L of them. Then if you want to connect them, so every pair gets path of length L minus 1 or L minus 1. The length and the order differ by 1, okay? Whatever, something like that, minus 1 plus 1. The theorem says that basically, if we have specified endpoints x and y, many of them, or shall we say not so many of them, L is large, so at most n over some polylog factor. Suppose that G expands well towards the remaining of the graph W. I will define precisely. Then, so the only important condition here is that G expands well. Okay, if G expands well, then we can find specific, then we can find path vertex disjointly that covers the whole vertex sets. We cover everything. Assuming this one, let's now look back to this leggy case. Assuming this one, basically now we want to apply it to here, right? We want to apply this theorem 6.7 to here. We embed all the remaining part of T, which is T double prime. Then we show that, okay, the remaining part still not so small. So we have this red expansion property, which I will define. That means then with this given pairs of endpoints, x and y, we can find the disjoint path of some given length that we want to cover all the remaining vertices. That will complete the embedding for this leggy case. Okay, the precise proof of theorem 6.1, assuming theorem 6.7 is not so long, it will be in my notes, I will send it to you. But basically, the idea is just what I sketch here by the picture. So I will not write down how you derive 6.1 from 6.7. It's quite, the picture speaks for itself, right? So the remaining, I will just define this condition. What do I mean by D expands into W? And then tomorrow we will sketch a proof for theorem 6.7. Okay. So basically this theorem says when we have this expansion property here, then we can cover, right? So exactly as it says here, we can cover expander with path and cover the whole vertex sets. So this notation, what is this? Basically, this is two conditions. For simplicity, we just give it a single name so we don't have to write two conditions all the time. This D expands into a subset. The definition is this. Oh, it's not 8. 6.3. So we're given the graph G, and we have a vertex set W. Okay, we say that G D expands into W if the two condition holds. First, we have small set expansion towards W. Okay, this is why this is the name, expands into. So if you take any set X of subset of G that's not so large, maybe it's good to verify. It's not subset of W, any subsets that's not so large, then you expand by a factor of D just within W already. Okay, expands into W. And the second one is this large set connectivity that we've always seen. If you take two sets large enough, you will see an edge. Okay, for any disjoint X, Y of size W over 2D. So when sets below W over 2D, it's when it's small, we expand by a factor of D into W. When you reach to W over 2D, then suddenly you have this large set connectivity, which is equivalent of saying that set of size W over 2D is expands hugely, because you can only have at most W over 2D non-neighbors, right? Otherwise, you will see always an edge. So basically, this D expands into W combines the small set expansion with large set connectivity. It's just more convenient to do it this way to define this. So for example, just to get used of this notation, if G D expands into itself, V of G, the whole vertex set, then it's the same as saying this is the same as saying that G is N over 2D joined large set connectivity, and it's a D N over 2D expander for sets of size and most N over 2D expands by a factor of D. It's the same thing, just that we combine these two notions. All right. What do I want to say? I think I will wrap up for today. Okay. So today we've seen that, just very quick recap. We've seen that the same proof for Feynman-Pippinger already give us this 5.6 or 5.7, which tells us that when you have some expansion, more precisely, when you have small set expansion here and large set connectivity, then we can embed almost spanning trees, which then can be used to determine the threshold for almost spanning trees in GMP, because this expansion property and large set connectivity is very easily verified for random graph. Turns out that the threshold is some constant over n, the same as having almost spanning cycles. Then we look at this problem of finding spanning tree, and since net connectivity of the whole graph is a necessary condition, we have to take P a lot larger now, not constant over n, but log n over n. And it turns out that constant times log n over n suffices to see all spanning trees of bounded degree. And what we're trying to do is to prove a weaker result, to prove for a single tree with a slightly larger probability up to polylog factor optimal. And for these, we say that we will treat trees differently when they have different structure. One is when it has lots of leaves, the leafy one, and one is when it has lots of long legs, this bare path. In both cases, we will remove either the leaves or the internal vertices of this bare path, which give us a much smaller tree and almost spanning. Then we can use the known result, in particular 5.7, to embed these almost spanning ones, right? And the remaining task in the first case is just to attach the star matching, which is quite easy because you can verify that the star matching can be found in random graph using some basic property of random graphs. So we will not talk about this case. We talk about the more challenging case when we have to find a path with given ends and specified length to cover a set of vertices that's left to be covered. This is essentially 6.7, saying that if we have some sort of expansion property, G is an expander, some sort, then we can cover it with path, the whole vertex sets. And we can even do better. This path has specified ends with specified length. Okay, so right, so I will stop here. Tomorrow we continue for the rest of the proof.
So anyone have any questions? So there are some questions on the chatting. It's 2 questions. It seems long. You can answer.
Oh, okay. Let me see. Dongyop is asking, so while the theorem gives an embedding result for fixed tree T, the proof seems to give universal embedding result for leggy spanning trees. Yes, you are right. For the leggy case, it gives universality because embedding T double prime, the 5.7 is a universality result. And embedding these trees, we use a deterministic pseudo-random expansion property. So that does not rely on the randomness. It also gives universality. For leafy trees, you have to verify. This is where you lose the universality for the leafy trees. The simpler case, but it can be done using, because the Richard proved it. But actually, I don't know how to do the leafy tree for universality. So
Also, there is one more question by Dongyu.
Here. Dongyu, does Montgomery's result imply that the threshold function Tn delta universality is C log n over n? Or do we need some more work to get this threshold function? So the threshold by its definition is when you're much bigger than this, you get that. When you're much smaller than that, you don't get that. So in that sense, in that definition, he determined the threshold, which is log n over n, right? So when C is sufficiently large, you see the universality. I think what you want to ask, do you mean the sharp threshold? That's open, actually. Here you see what I write down here, that C depends on delta. It might very well be the case that there exists a universal constant, could be even 1, such that when you have P equal to 1 plus epsilon times log n over n, you see all the bounded degree spanning tree. Okay? I think this constant 1 holds for certain type of trees. I don't quite remember which type. One of leafy or the leggy tree, something like that. And for the other type, we don't know this constancy.
Any other questions?
Is there any special reason why local global property arises?
Is there what did you ask?
I mean, is there any some intuition or some
intuition? Okay. I don't know how to answer this question. I think so. What we're hoping, we say that when you don't have local obstruction, some necessary local obstruction, then in the nice case, we should see some global structure, right? For example, when you don't have isolated vertex, then in the nice case, the graph becomes connected. So we hope this nice global structure happens. And in order to have this nice case, then usually the graph has to be nice itself, right? So the randomness in the sense is nice. It has lots of the properties that we expect it to have. So this is maybe that's one way to say it. I don't know how to. In other areas, there's also this local global thing, right? For example, in number theory, when you have no local obstruction, meaning that if you don't have solutions modular some fixed P, then if you don't have local obstruction, then globally you are no problem, right? So yeah, so I don't know how to answer this question.
Any other questions? If not, then we can finish the lecture here and then meet tomorrow for the last lecture. So yeah, Hong, thank you for your nice lecture.
Thank you for being here. So I will see you guys tomorrow.
Nice lecture. Thank you.